Boring mathematics for sleep. The forgotten math that built the pyramids. Welcome, sleeper. Hello, you made it. You've arrived at a video about ancient Egyptian mathematics, which means one of three things. Either you're very curious, you're very tired, or you're very weird, all of which are perfectly acceptable here, especially the last one. Now, before we begin, I want you to take a moment. Maybe you're lying in bed. Maybe your eyes are already half closed. That's good. That's the goal. Because even though we're going to talk about numbers and ancient civilizations and mysterious triangles buried in the desert, you don't have to remember a single thing I say. Not a single number. Not a single date. Nothing. Now, let's talk about something truly ancient. Older than Rome. Older than the Greeks. Older than math homework. Egypt. Egypt is that one civilization that somehow has remained cool for 5,000 years straight. Giant stone pyramids, gold-covered tombs, gods with falcon heads, and enough sand to bury several large countries. You know, the classics. But here's what people don't always realize. The pyramids, those perfectly angled, mind-bending structures, weren't just built with brute force and slaves dragging rocks up hills. No, they were built with math. But not the math you know. The Egyptians didn't have calculators, or algebra, or symbols like X and Y. They didn't even have zero. Think about that. No zero. Just try doing math without it. It's like trying to write a novel without using the letter E. It's possible, but absolutely bonkers. And yet, without any of the tools we take for granted, they built monuments so precise that modern engineers are still kind of confused. Like, wait, how? That's what we're going to explore tonight. This is not a lesson. This is not a lecture. This is a journey. A very sleepy journey. Through time, through sand, through numbers. The kind of numbers that are carved into stone, not scribbled on whiteboards. Now I know what you're thinking. Or maybe you're not thinking anything. Maybe you're already drifting. That's fine. That's ideal. But if you are thinking, you might be wondering, what kind of math are we talking about here? The answer is ancient, dusty, sometimes confusing math. The kind that was invented to solve very practical problems, like how many goats does this farmer owe in taxes? Or how do I know where my land ends after the river floods and erases everything I own? Or my personal favourite, how many beers does a pyramid builder need to be paid for a day of hauling 2-ton stones in 40-degree heat? Yes, we're going to talk about pyramid beer wages. But before we get to the really juicy parts, and trust me, there are some very juicy hieroglyphics in your future, we need to lay some sand-covered foundations. We're going to start with the Nile. Because without the Nile, there is no Egypt. There is just sand. A lot of it. The Nile was the lifeline. Every year, it would flood. And every year, it would leave behind rich black soil. Perfect for crops. Also perfect for chaos. Because when the river wipes out all your property lines, you suddenly need a system for redrawing who owns what. Enter geometry. But we'll get to that. We're also going to meet the scribes. The nerds of ancient Egypt. These guys were trained from childhood to read, write, and most importantly, calculate. If you were a scribe, you could live pretty well. People feared you, mostly because you could read contracts and taxes, and you understood fractions, which scared most of the population. Honestly, not much has changed. We're going to talk about how they counted without place value, how they made rectangles out of ropes, how they used body parts to measure buildings. Yes, body parts. Their measuring system involved palms, fingers, elbows. The whole thing was basically a walking calculator with sandals. We're also going to get weird. We're going to talk about sacred numbers, like 3, 4, and 7, and how certain shapes were considered magical. We'll talk about how math was used to build tombs aligned with the stars, and how those tombs were designed to last not just forever, but beyond forever, because if you're planning your trip to the afterlife, you want good architecture. And yes, Eventually we'll get to the pyramid itself. The big one. The Great Pyramid of Giza. The one with the absurdly accurate corners and the maybe not appearance of the number pi in its dimensions. Because nothing screams math mystery quite like ancient pi. So that's the plan. We'll go step by step, brick by brick, number by number, but never fast, always slow, always calm, like the slow unfolding of a linen scroll in the candlelight, or the endless shuffle of sandals across stone floors in a forgotten temple. And don't worry if you miss parts. That's the point. This is not a video you pass a test on. This is a video that tucks you in. So, welcome to the forgotten math that built the pyramids. A place where numbers were sacred, where geometry was divine, and where nobody had ever heard of a calculator. But they still managed to build something that no one's managed to top. Let's begin. The Nile and the numbers. The Nile was everything. That's not an exaggeration. It wasn't just a river. It was the calendar, the grocery store, the highway and the office water cooler of ancient Egypt. If the Nile was in a good mood, Egypt thrived. If it was in a bad mood, people panicked. You might think ancient Egyptian math came from priests sitting around being all philosophical. No, it came from farmers going, wait, where did my field go? Every summer, the Nile flooded, and every autumn, it went back down. But when it receded, it didn't politely leave everyone's farmland, exactly where it found it. No, it rearranged everything like a toddler with a box of Legos. So suddenly, after the flood, you had people arguing, that's my plot of land. No, it's mine. No, that rock is definitely new and it's on my side. Chaos. Muddy chaos. And what's the best way to solve chaos? Invent math. That's right, geometry, at its root, was invented to redraw property lines. It wasn't about discovering universal truths. It was about figuring out where to plant your onions without getting into a fist fight with your neighbor. Imagine the scene. Scribes with ropes. Farmers yelling. Some guy trying to bribe the land measurer with a goat. All very organized. Very civilized. But the Nile didn't just steal your property lines. It also decided when you could eat. Flood season meant planting season was near. No flood? No crops. No crops? No bread. No bread. Everyone cries. So early Egyptians needed to track the Nile's behavior. They needed to know when it would flood, and not just sometime in summer, but roughly when the water would start rising. That meant observing the sky, watching the stars, basically turning nature into a giant cosmic wall calendar. That's how they discovered that when a bright star, Sirius, appeared just before sunrise, the flood was coming. That's right. The new year in Egypt started not with fireworks, but with the star Sirius blinking, hey, just before dawn. So they started building calendars. And for calendars, you need numbers. You need months, days. Even if your weekend is more of a concept than a thing. The ancient Egyptian year had 365 days. Just like ours. Sort of. They had 12 months of 30 days, which is only 360. So they just added 5 bonus days at the end. Festival days. Days outside the calendar, which is either genius or cheating, or both. These days were for celebrating the gods' birthdays. Yes, even the gods got birthday parties. With cake? Probably not. With beer? Absolutely. Now, let's talk about how they actually counted, because the ancient Egyptian number system is unique. Imagine if Roman numerals and stick figures had a baby, and that baby was kind of cute but also very impractical. They had symbols for 1, 10, 100, 1000, 10,000, and so on. 1 was just a straight line, 10 was a heel bone, 100 was a spiral, 1,000 was a lotus flower, 10,000 was a pointing finger, 100,000 was a frog, and 1,000,000 was a man with his arms in the air, like he just found out he won the lottery. So to write 3041, you'd need 3 lotuses, 2 spirals, 4 heel bones, and 1 straight line. Sounds peaceful, until you realize that if you want to add 2 numbers, you're literally counting pictures. It's math through interpretive dance. And did they have 0? Nope. 0 wasn't a thing yet. Which is weird, because 0 is kind of essential. But for them, if something didn't exist, they just didn't write anything. 0 was more of a philosophical idea, like, don't worry about it, this makes basic math harder. Try subtracting 1000 from 1000 when you don't have 0. The answer is nothing, but there's no nothing to write. So you just leave it blank and hope nobody asks too many questions. Still, their system worked, especially for keeping track of stuff, which, let's be honest, is the real reason math was invented in the first place. Take grain. In Egypt, grain was currency. You could pay workers in grain, pay taxes in grain, pay priests in grain. People loved grain, probably more than cats. Maybe. So you needed to count it, measure it, store it, and most importantly, tax it. That's where the scribes came in. The scribes were the math elite. They trained for years to master writing and counting. They had to memorize thousands of symbols, but they also knew how much grain a person should produce, how much water a field needed, how long a canal should be to irrigate a crop. These were not just dusty scroll nerds. These were logistical masterminds. You might picture them sitting in temples doing rituals, but really they were out in the field with measuring ropes, checking harvests, calculating rations, and occasionally explaining to someone that no, you can't claim your neighbor's goat as a tax deduction. And they didn't just work for pharaohs. They worked for temples, for merchants, for big construction projects. And when I say big, I mean pyramid big. But we're not there yet. First, we're still with the Nile. Still in the early days, when math was a tool, not a subject. A tool for solving problems. Like how much food will we have next year? Or how many workers do we need to build that thing that Pharaoh won't stop talking about? It was math for survival. Math with purpose. Math without numbers as we know them. So next time someone tells you math is boring, tell them this. Math literally kept people alive. It told them when to plant, when to store food, when the gods were probably going to party, and when the taxes were due, which, let's be honest, is still when the panic sets in. And all of it started with the river. The Nile wasn't just a body of water. It was a mathematical event. A yearly, predictable, terrifying, generous, floody event. And it forced people to think, to plan, to measure. Next up, we'll talk about how people did math before they had actual math. Like tally marks, knots in ropes, and whatever you call counting on your fingers when you don't yet have a word for finger. Let's talk about something weird. What if you had to do math, but you didn't have math? No numbers, no symbols, no written system, no multiplication tables, no calculator, not even a whiteboard to dramatically scribble on. Just life, and problems to solve. That's what it was like for early humans, and for the early Egyptians too, before they started carving symbols into stone, and yet, they still counted things. They still measured things. They still divided, and estimated, and made decisions, which means they had math. Just not the kind we'd recognize. This is what we call proto-mathematics. Math before math. Math in the wild. Math with no shoes on. Imagine a farmer with a bunch of sheep. Let's say 15 sheep. He doesn't know the number 15. He doesn't know the word sheep, but he does know what his herd looks like when it's full. And if one goes missing, he notices, because something's off. That's counting, sort of. That's one of the first kinds of math, recognizing sameness and difference. Knowing that a certain pile of stuff is supposed to be this big, and now it's not. Early humans used tally marks. You've seen them. 1 line, 2 lines, 3 lines, 4. then a slash through all four to make 5. Boom. Primitive Excel spreadsheet. They would scratch these onto bones, stones, sticks. If they had a particularly exciting day, like trading goats or surviving a flood, they'd make a new mark. It's like journaling, but with less drama and more livestock. One of the oldest tally records ever found is the Ishango bone, discovered in Central Africa. It's over 20,000 years old. It has a series of notches carved into it, in groupings that suggest not just counting, but even some kind of multiplication or doubling. This thing is basically humanity's first math homework, and it's a bone, because nothing says prehistoric math like scratching equations onto femurs. But the Egyptians didn't stop at tally marks. No, they had to level up. They started using tokens, little clay shapes that represented goods. One token meant 1 jar of oil, another meant 1 sheep. If you wanted to store value or track what someone owed you, you'd put the tokens in a pouch. These pouches eventually became clay envelopes, which sounds adorable, but were actually sealed containers. If you broke one open, you could check what was inside, which is both security system and receipt. Ancient Egypt, inventing locked packaging before Apple. Eventually, they realized they could just press the symbols of the tokens onto the clay envelope and skip the pouch entirely. And just like that, writing was born. First for counting, then for storytelling, then for drawing little boats on the side of tombs. But tokens and scratches weren't always enough. Sometimes you needed bigger numbers. You needed to measure things, like land, or grain, or how long it takes a guy to walk across a field while yelling at birds. So they invented measuring ropes. That's right, ropes, with knots. These ropes were marked with evenly spaced knots. You could stretch one across a field and count the knots. 10 knots, 10 units of land. Done. You could measure how far, how wide, even how diagonal something was. One of the coolest tricks, the 3-4-5 triangle. Here's how it worked. You take a rope with 12 evenly spaced knots, then you arrange it into a triangle where one side has 3 units, one has 4, and one has 5. Bam. Perfect right angle. This isn't just a math trick. This was land surveying technology. It was also kind of magic to people back then. Make a rope triangle, and suddenly things line up. The gods must approve. It gets even better. These rope stretchers weren't just random guys. They had a name, Harpti Napte. Try saying that 10 times fast. Or just once, slowly, in a mysterious whisper. Harpti Napte. They were professionals, rope scientists, measuring the land after the Nile flooded every year, re-establishing property lines, bringing order from watery chaos. And they did all of this without using equations, just ropes and knots and patience. Of course, not everything was ropes and bones. Sometimes you just used your body. That's right, your actual limbs were a measuring system. Why invent rulers when you already have arms? The Egyptians measured using cubits, which was the length from your elbow to the tip of your middle finger. That's your cubit. Unless you're a pharaoh, then it's your royal cubit, which is longer, because everything royal is fancier, including elbows. They also had palms the width of 4 fingers, digits the width of a finger, and spans from thumb to pinky when you stretch your hand wide. So a building might be 100 cubits long, 30 cubits tall, and 10 palms wide, plus or minus one angry architect. It wasn't precise by modern standards, but it worked, especially when everyone used the same arm. And that's kind of the point. The Egyptians didn't need symbolic math the way we do today. They just needed ways to solve problems. Need to store grain? Use baskets. Count the baskets. Done. Need to dig a canal? Use ropes. Measure the distance. Dig. Need to split food among workers? Grab a stick and draw some pictures in the sand. It was math made for doing, not thinking. And there's something beautiful about that. No symbols, no formulas, Just clever humans figuring stuff out with bones, ropes, fingers, and mud. So the next time you forget how to calculate something, remember the Egyptians probably just used a knotted rope, pointed at the stars, and called it a day. In the next chapter, we'll dive into how Egyptians finally wrote their numbers, and how their counting system was both brilliant, kind of annoying, especially if you hate drawing frogs. Counting like an Egyptian. Okay, we've scratched on bones, we've tied knots in ropes, we've measured things with elbows and fingers. Now it's time to level up. Let's talk about numbers. Not just thinking about how many goats do I have, but actually writing it down, on papyrus, or a wall, or a pot, if that's all you had. The ancient Egyptians had a number system, a real one, with symbols and everything, but calling it efficient would be generous. Let me explain. Egyptian numbers were written using hieroglyphs. And no, not the complicated ones with falcon-headed gods and ankhs everywhere. These were the basic, boring ones. The numbers. They had separate symbols for 1. Here's how it looked. 1 was a single stroke. Just a vertical line. Simple. 10 was a drawing of a heel bone. Why a heel bone? Who knows? 100 was a spiral, possibly representing rope. Possibly a cinnamon bun. 1000 was a lotus flower. Very elegant. 10,000 was a finger pointing. Helpful. 100,000 was a tadpole, or a frog, depending on how artistic your scribe felt. And 1,000,000, a guy with his arms raised in celebration, or panic. Or maybe he just really liked big numbers. So let's say you wanted to write the number 3423. 3 lotus flowers, 1000, 4 spirals, 100, 2 heel bones, 10 each, 3 strokes, 1 each, and you'd stack them all together, in no particular order, just grouped by type. It was like emoji math, but harder to text. There were no place values, no columns, just symbols. The more symbols, the bigger the number. So if you wanted to write 99,099, well, you'd better clear your afternoon. This system is called additive. You just add up the symbols you see. There's no subtraction involved, no clever tricks. It's brute force math. If you want 5, you write 5 strokes. Want 746. Get ready to draw a parade of spirals, lotuses, heel bones, and frogs. Sounds slow? That's because it was. But here's the thing. It worked. Most people weren't doing algebra. They were tracking taxes, counting bread, estimating bricks. You don't need a TI-84 for that. You just need to know how many frogs you've drawn so far. Also remember, they had no zero. Zero wasn't part of their system, not even as a placeholder. So if there was nothing in a number, they just didn't write anything. For example, 1 would be a spiral, 100 and a stroke 1. No symbol for the 0 in between. You were just supposed to understand it was there, which is kind of impressive. Or terrifying, depending on whether you're the person writing or the person decoding. Now, imagine doing math with this system. Let's say you want to add 2 numbers. Easy. Just draw all the symbols for the first number, then draw all the symbols for the second number, then count how many total you have of each symbol, and write that down. It's like playing with Lego bricks. Add all the red ones, then all the blue ones, then hope you didn't lose any under the couch. Subtraction? Slightly worse. You cross out symbols from the bigger number until what's left is the difference, which is fine until you're dealing with a number like 7 to 321, and suddenly you're crossing out tadpoles and heel bones like your life depends on it. And multiplication? Hoo boy. The Egyptians didn't multiply the way we do. They used a method called doubling. Let's say you want to multiply 12 by 7. You write a table, start with 1, then 2, then 4, then 8. Doubling each time. Alongside that, you write the doubles of 12. So 12, 20.
Now, you look for which numbers on the left add up to 7. In this case, 1, 2, and 4. That makes 7. Then, You add the matching numbers on the right, 12.
Boom. 12 times 7 is 84. Math magic. Was it fast? Not really. Was it clever? Yes. Was it fun? Probably more fun than hauling stones. This doubling method worked for division, too, just in reverse. Trial and error, baby. The Egyptian way. They also had a very strange love affair with fractions. And I mean weird. Egyptian fractions were almost always written as unit fractions. That means every fraction had a numerator of 1, so instead of writing 2, 3, they wrote 1, 2, pole 1 to 6. Because apparently 2, 3 was just too obvious. They'd break down any fraction into a sum of distinct unit fractions, no repeats allowed, like some kind of strange fraction puzzle. So 3, 4 became 1, but 5, 6. That's 1, 2, Punsima 3. Clean, tidy, slightly irrational, but 4, 5. Now it gets weird. That becomes 1, 2, pole 1, and it wasn't just about preference. This was how everyone did it. Every scribe, every tax record, every bread recipe. If you needed 2, 7 of something, you'd better be good at weird math. Why did they do this? Honestly, no one knows for sure. Some say it was tradition, some say it was easier for practical division like cutting bread or cloth. Others say because Egypt. Whatever the reason, it's what they did, and they did it well, even if it makes modern mathematicians twitch a little. So yes, their number system was slow, it was clunky, it had no zero, it made fractions unnecessarily dramatic, but it also helped build temples, track time, pay workers, measure the stars, and move mountains, or at least large limestone blocks. It wasn't math like we know it, but it was math that got stuff done, and sometimes that's the best kind. In our next chapter, we'll meet the scribes, the ancient math nerds who made all of this possible, the ones who memorized every frog, every spiral, every fraction and got paid in beer. You're going to like them. Scribes, the OG math nerds. Every great civilization has its nerds. Rome had philosophers, Greece had mathematicians with beards, and Egypt had the scribes. Scribes weren't just writers, they were calculators, accountants, statisticians, architects, librarians, and the ancient world's version of a human spreadsheet, all rolled into one person, usually wearing a linen kilt and squinting at papyrus. Let's be clear, being a scribe was a big deal. In a world where most people couldn't read or write, scribes were like wizards. Except, instead of casting spells, they calculated tax returns, which, depending on your view of taxes, might still count as dark magic. So how did one become a scribe? Well, first you needed to be born lucky. Scribes were almost always from upper or middle class families. You couldn't just wander in from the fields one day and say, "Excuse me, I'd like to become a master of the number frogs." You needed connections and education, which started young. Training as a scribe could take years, literal years of sitting in dusty classrooms, copying out symbols, practicing fractions, learning how to multiply the Egyptian way, which, as we now know, involves a lot of doubling and very little mercy. They learned hieratic writing, the shorthand version of hieroglyphics. It was faster, simpler, and perfect for scribbling numbers while the person next to you loudly argues about grain taxes. Scribes had to memorize thousands of symbols, thousands, each with specific meanings, uses, and rules. It was like trying to learn a language where every word is also a tiny bird or a weird eyeball. Fun. But if you made it through the training, you got access to one of the best gigs in Egypt. That's right, scribes didn't do manual labor. No brick hauling, no ditch digging, no standing in the sun while your eyebrows melt off. They worked in the shade with pens and numbers. Some were assigned to government offices, others worked in temples, some travelled with armies, and many scribes were assigned to pyramid construction sites, because when you're moving millions of stones, Someone has to keep track of the receipts. Let's imagine this for a second. You're a scribe. You've been sent to Giza to oversee part of the pyramid project. Your job? Make sure each delivery of limestone is counted, that workers get their daily rations, and that the ramps don't collapse because someone forgot how angles work. Every morning, someone hands you a list, written in symbols, and you do the math. You calculate how many jars of beer to give out. You write down how much copper was used in chisels. You update payroll, which was usually paid in bread, onions, and alcohol, because yes, workers were often paid in food and drink. A good day's work might earn you 4 loaves and 2 jars of beer. And who managed that math? You guessed it, the scribes. Some scribes specialized in land surveys. They'd go out after the Nile flooded and remeasure fields, with ropes, with cubits, with patience, and with a strong sense of please don't stab me. I'm just here to measure your onions. Others were tax scribes. These guys had the unfortunate job of collecting goods from farmers. Picture someone walking up to you with a clipboard and saying, hello, the gods require 30% of your wheat. Not exactly the village favourite. There were also medical scribes. They wrote down treatments, symptoms and magical spells, because medicine in ancient Egypt was a fun mix of real herbs, spiritual chants, and occasionally putting a dead mouse on the wound. Don't try that at home. But no matter what kind of scribe you were, you had power. Knowledge was rare, and you had it. You could read laws. You could calculate debts. You could track supplies. If someone tried to scam the system, you'd be the one to catch it, or cover it up, depending on how generous the bribe was. Now let's talk about the tools of the trade. A scribe carried a writing kit, usually made of wood. Inside, a small palette with ink, black for normal writing, red for headings or warnings, a reed brush or pen, a roll of papyrus, and maybe a snack, because all good nerds carry snacks. They'd sit cross-legged, with the papyrus on their lap, writing in tiny, perfect script. If you've ever tried to write neatly on paper without a desk, you know this is a form of torture. But they did it, day after day. And they didn't just record facts. They preserved stories, wisdom, math problems, poetry, legal contracts, even jokes. Yes, jokes. There are Egyptian papyri with jokes in them, mostly about donkeys or flatulence. Honestly, not much has changed. Some scribes became so legendary that their names were remembered for centuries, like Ames, who copied the famous Rhind Mathematical Papyrus, one of the oldest known math documents. He didn't claim to invent anything. He said he was just copying it from older sources. That's right, even ancient math homework was copied from someone else's homework. There's also the Moscow Mathematical Papyrus, which includes geometry problems. One of them is about calculating the volume of a truncated pyramid. So yes, ancient Egyptians not only built pyramids, they did math about pyramids. Because sometimes, building one isn't enough. You've got to write a word problem too. So how important were the scribes? Put it this way, Egypt wouldn't have worked without them. Not just because they did math, but because they kept order. They wrote down who owned what, who paid what, who owed what. And when someone important died, scribes wrote the prayers that would help their soul navigate the afterlife. That's a lot of pressure for a guy with a reed pen. And they did it all with patience, with discipline, and probably a sore back from sitting on stone floors all day. Were they flashy? No. Did they wear gold and swing swords? Also no. But did they quietly run the entire empire with ink and math? Absolutely. So next time you picture ancient Egypt, don't just think about the pharaohs and the pyramids. Think about the quiet guy in the corner scribbling away, calculating bread rations, and mumbling something about frogs and unit fractions. Because without that guy, the pyramids might never have been finished, or aligned, or paid for. And now, we're ready to draw lines in the sand. literal lines. With ropes, because next we enter the world of ancient Egyptian geometry. Brace yourself. There will be triangles, straight lines in the sand. Let's go outside. Not really, of course. You can stay cozy wherever you are. But mentally, let's step into the Egyptian sun. It's hot. The sky is blindingly blue. The ground is sand, and more sand. And then for variety, some slightly different sand. Now, imagine you're holding a rope, a long one. It has knots in it. Not randomly tied knots, but spaced carefully, evenly. You're standing next to another person, also holding a rope. Maybe a third person joins, and together you stretch this rope across the ground. Congratulations, you're a rope stretcher. In ancient Egypt, that made you kind of a big deal. The rope stretchers, or hoptonapti, if you want to sound fancy and slightly Greek, were surveyors, early geometers, the unsung heroes of architecture. They took something chaotic, like a huge empty plot of desert, and gave it structure, with rope. Here's why they mattered. Every year the Nile flooded. We've said that. But when it flooded, it didn't just water the crops. It erased everything. Property lines, farm boundaries, that nice corner where you used to grow leeks, gone, washed away like a sand castle. So, someone had to come back and measure it all again, redraw the land, decide who owned what, and make sure nobody ended up with an accidental goat. But how do you make a straight line in sand? No rulers, no lasers, just rope and shadows, and a lot of sunburn. The trick was in the rope's knots. Let's say you want to make a right angle, 90 degrees, perfect for buildings, ramps, altars, and dramatic corners. You take a rope with 12 evenly spaced knots, creating 13 segments. Then you form a triangle with sides of 3, 4, and 5 units. Boom, that's a right triangle. You've just created a perfect 90-degree angle using only string and walking around in a triangle. Why does that work? Because of a simple rule you might remember from school, the Pythagorean theorem. A squared plus b squared equals c squared. But here's the fun part. Egypt used this trick long before Pythagoras was even born, like over 1,000 years before. So maybe it should be called the Egyptian theorem, or rope angle deluxe, or just the thing that saved ancient buildings from being weirdly crooked. This method was incredibly useful. You could map out corners for buildings, design roads, lay the foundations for temples and tombs, even calculate land for taxes, which, let's be honest, was probably the real motivation. Pharaoh always gets his cut. Rope geometry wasn't just about angles though. It was about space, about understanding how land was shaped, where it began, where it ended, and how to turn chaotic nature into neat, useful rectangles. They used triangles, squares, and rectangles, all measured by ropes. Sometimes they'd stretch the rope between sticks in the ground, sometimes between stones, and if the rope was long enough, they could use it to measure fields, or align walls, or walk dramatically across the desert, pretending to be important, which, if you're carrying math rope, you kind of are. Now imagine doing this in a huge open space. Just you, your rope, and the sun. You press your footprints into the dust. You adjust your knots. You pace it out again. You check the shadows. You stretch the rope tighter. You mark a spot with a stone. And then someone behind you says, "Are we sure this is north?" Because here's the other thing. The Egyptians cared about alignment. They didn't just build randomly. They aligned their temples and pyramids with the stars, with the sun, with cardinal directions, north, south, east, west. Everything had meaning, and the rope stretchers helped make that happen. Sometimes they'd use shadows to find true north. Plant a stick in the ground, track the shadow over the day, draw a curve from its movement, and use that to find a perfect line. This was practical astronomy. No telescopes, just the sky. and sand, and a surprising amount of cleverness. And this geometry wasn't just used for big state projects. Farmers used it, architects used it, priests used it to position altars and sacred spaces. Geometry was everywhere. It was how order was made out of natural chaos. Now, you might be wondering, where's the math in all this? Well, it's not written as equations, but it's still mathematical thinking. You're observing, measuring, using logic, creating shapes, predicting outcomes. That's geometry. That's real math, without a single digit, written down, and it worked. The proof? Look at the pyramids. Perfectly squared bases, nearly flawless alignment, slopes that are consistent, corners that still hold up thousands of years later. All that began with someone stretching a rope in the sand. Let's also take a moment to appreciate the poetic side of this. You're literally drawing lines on the earth, marking the desert, turning wild, endless sand into structured, meaningful space. That's more than measurement. That's art.
In many ways, geometry for the Egyptians wasn't just math. It was a way of understanding the world, making sense of divine order, bringing harmony between heaven and earth. A rope, a shadow, a triangle, and suddenly, the universe makes just a little more sense.
So the next time someone tells you that geometry is boring, tell them this. Geometry is how ancient people turned sand into civilization. It's how they made the invisible visible. It's how they told the gods, look, we understand a little something now. And it all started with a rope. In the next chapter, we'll talk about what happened after those floodwaters came and washed everything away, and how Egyptians used geometry not just to measure land, but to literally rebuild the world every single year. It's like spring cleaning, but with triangles. The geometry of rebuilding the world every year. Imagine this. Every year, without fail, your entire world gets deleted. Not metaphorically, literally gone.
Your backyard vanished. Your field where you grew onions and emotionally argued with ducks, gone. Your fence, your footpath, that weird rock you used as a chair, all underwater for weeks.
Then, one day, the water goes away. And what's left? Mud. Wet, soggy, unrecognizable mud. This was normal in ancient Egypt. The Nile did this every year. Flood in, flood out, reset button. Like nature was saying, let's try this again. The Egyptians didn't see this as a problem. They saw it as a cycle, a divine rhythm. Flood, grow, harvest, flood again, and in between, rebuilding, remeasuring, re-owning your life. Which brings us to one of the most underrated superpowers of the ancient world, applied geometry. After the Nile flood, nothing looked the same. Property lines had been washed away. The nice little rectangle where you planted flax. It now looks like abstract art, and your neighbour, Snufferoo, swears that the prime corner where the palm tree grows has always been his. Liar.
What do?
You call in the rope stretchers. They come out with their measuring ropes, maybe a cubit rod, and they start laying out lines, straight ones, right angles, triangles, rectangles, marking land as it once was, or as close as anyone can agree it was. It was like redrawing the map. Every year. And it wasn't just for personal farms. The pharaoh owned massive lands. Temples had sacred gardens. Priests needed exact spaces for rituals. The math wasn't optional. It was everything. Let's pause for a second to appreciate the patience involved here. Imagine being a scribe or a surveyor. You spend all spring and summer carefully documenting everyone's land. You measure, you record, you make little maps. You feel proud, organized, in control. Then the river floods and laughs in your face. All that work, useless, and now you have to go out and do it all over again. While people yell about barley and sacred boundaries and "but my cousins swore this was mine," you wouldn't blame a scribe for just giving up and moving to a nice quiet cave. But they didn't. They came back, year after year, with rope, And with this annual chaos came innovation. Egyptians got good at geometry because they had to. Every flood was a math test. Every year was a pop quiz in land reclamation, and failing meant either someone lost their harvest or got stabbed with a measuring stick. Probably metaphorically. Hopefully. This process is one reason why Egypt developed geometry earlier and more deeply than most other places. They weren't just curious. They were responding to the Nile's annual delete and refresh button. Geometry became practical, urgent, sacred. Now let's talk about tools. We've already met the rope, with its evenly spaced knots, but there was also the cubit rod, a literal stick marked with cubits, palms and fingers, often made of wood or stone. The ultimate measuring stick. They'd use the rod to check lengths, check alignments. Some were incredibly fancy, carved with symbols, measurements, even the names of kings. If you were a temple scribe with a gold inlaid cubit rod, you were basically the Beyoncé of measurement. Then there were plumb lines, strings with weights to find verticals, and levels using shallow trays filled with water to make sure surfaces were flat. All this to make things right again. And let's not forget the spiritual side. In Egyptian belief, Mast was the goddess of order, balance and truth. When you restored land after chaos, when you brought things back into harmony, you were doing Mast's work, literally restoring balance to the world. So yeah, surveying wasn't just a technical job, it was cosmic. Now picture this. A rope stretcher stands on a muddy field, sun rising behind him, rope in hand. He plants a stick in the ground, measures an angle, marks a corner. People gather, watching. Maybe a priest nods in approval. Maybe a goat walks across the plot and ruins everything. Still, the work goes on. He draws a rectangle in the sand, and just like that, a family's farm is reborn. It's beautiful, in a way. This silent geometry, restoring land, restoring life. Even today, this concept feels familiar. Think about it. Your inbox floods, your desk explodes, your calendar gets wiped clean by life. And what do? You measure, you sort, you organize, you rebuild. Every year, every season, every Monday morning, we are all tiny Egyptian rope stretchers, bringing order to our own personal chaos. But back in ancient Egypt, it was more literal, more immediate, and way muddier. There's something poetic about it. The river destroys so that things can be measured again. The world becomes shapeless, so you can shape it. And the rope, the triangle, the line in the sand, that's how you reclaim your place in the universe. So next time you feel overwhelmed, just remember, the Nile flooded every year, and people still showed up with rope. In our next chapter, we'll look at how Egyptians began measuring something even trickier than land, time, with nothing but a stick and a shadow. Because when the sun is your clock, things get interesting. The shadow clock and the length of day. Let's talk about time, not the deep philosophical kind where we all start questioning our existence, just regular, everyday, when is lunch kind of time. Because even in ancient Egypt, people wanted to know what time it was, when to start work, when to feed the goats, when the priest would start chanting loudly, when to stop measuring things with ropes and go sit in the shade. And here's the twist. They had no clocks, no ticking, no talking, no bells, no notifications, no snooze button. So what did they do? They used the one timekeeper they could always rely on, the sun. Now, if you've ever stood outside on a sunny day and looked at your shadow, you might have noticed it changes. In the morning, it's long. Around noon, it shrinks. In the afternoon, it stretches out again, but in the other direction, and by sunset, it's gone. To the ancient Egyptians, this wasn't just fun shadow play. This was data, time information, straight from the sky. So they built a device, a very fancy name for a very simple thing. It was called a shadow clock. You might know it by another name, a sundial, but before sundials got all round and sophisticated, they started with something very basic. A stick, planted in the ground. That's it. This stick, called a gnomon, cast a shadow, and as the day passed, the shadow moved. The Egyptians noticed this. They observed that the shadow shifted in a predictable arc, that the length of the shadow told you how high the sun was, that the direction told you what part of the day it was. And then they started marking the ground. They watched the shadow throughout the day, drew lines in the sand to track its movement. They began to divide the day into parts, not hours like we know them, but segments. Eventually they developed tools, flat, L-shaped devices with hour marks. These were the original shadow clocks. Simple, portable, brilliant. You'd point it toward the east in the morning, west in the afternoon, and read the shadow's position to tell the time. It wasn't precise, but it worked. Now here's where it gets interesting. You see, Egyptian hours weren't like ours. They didn't divide the day into 24 fixed units like we do. Instead, they had 12 hours of daylight and 12 hours of night. Always. Sounds normal, right? But here's the twist. In summer, the days are longer. In winter, they're shorter. So in Egyptian time, an hour could be longer or shorter depending on the season. Your hour in July might last 65 minutes. In December, maybe 45. It's like living inside a stretchy clock. And everyone just accepted it. No one yelled, "Wait, why is my hour only 47 minutes today?" They understood that time was tied to nature, to the sun, not a machine. Honestly, that might be healthier than what we have now. Imagine that. Waking up and knowing your schedule literally changes with the seasons. Like, sorry I'm late, it's winter, the hours are shorter, and people would just nod and say, "Ah yes, reasonable." Back to the Egyptians. They didn't just track shadows for fun. Timekeeping had serious purposes. In temples, rituals had to happen at specific times of day. If you offered something to a god at the wrong hour, that could be bad, like very bad. Divine judgment bad. So priests relied on shadow clocks and star positions to stay on schedule. They even had night clocks, tools based on the rising and setting of certain stars to keep track of time after sunset. These tools were often reserved for the elite, the educated, the ones who needed to know what time it was for religious, political, or engineering reasons. Because yes, engineering. When you're building something like a pyramid, knowing how much daylight you have is kind of important. You want to time shifts. You want to plan deliveries. You want to make sure no one drops a 2-ton stone block in the dark. So the sun wasn't just a god. It was the world's most reliable supervisor. Let's pause here and imagine the scene. You're in the desert. It's morning. A long shadow stretches across the sand. You draw a line. A worker walks by and asks, "What time is it?" You point at the shadow and say, "Third line." He nods and walks away. No arguments. No minutes. Just shadow logic. There's something deeply peaceful about that. Now, you might ask, did they have calendars? Yes. In fact, they were among the first to invent a 365-day calendar, based on the movements of the sun and the flooding of the Nile. Each year had 12 months of 30 days, plus 5 extra days at the end. These were like bonus days, festival days, outside the regular calendar. You could eat, drink, and pretend deadlines didn't exist. Glorious. But for daily life, they didn't have wristwatches or reminders. They had the sky, and they read it like a book. Shadow clocks were only the beginning. Later, they would invent water clocks, bowls that dripped water at a steady pace to measure time. But that's another chapter. For now, picture this. A group of scribes, a flat piece of stone, a small L-shaped clock, the sun rising behind them, the shadow creeping forward, marking time in silence. A day beginning. No ticking, no alarms, just sunlight, sand, and a line. It wasn't precise, but it was enough. And sometimes, enough is perfect. In the next chapter, we'll go even higher, because what do you do when you want to align your temple, not just with the ground, but with the stars? That's right, we're heading to the heavens. Get ready to meet Orion, Sirius, and a sky full of sacred geometry, measuring heaven for Pharaoh. Let's leave the ground for a bit. We spent a lot of time in the mud, the fields, the sand, measuring land, drawing triangles, chasing shadows. But now, let's look up, because the ancient Egyptians didn't just measure Earth, they measured heaven, and not just for fun, not just for curiosity, but for something bigger, something eternal. They believed the sky was a map, a calendar, a message board from the gods. And if you wanted to build something truly sacred, like a temple or a tomb or a great pyramid, you had to align it not just with the land, but with the stars. Let's start with the basics. The Egyptians were expert sky watchers, long before telescopes, long before star charts. They watched the night sky with their eyes, their memory, and their patience. They noticed patterns, stars that rose and set at the same times every year, constellations that moved like clockwork, and they began to associate certain stars with seasons, with events, with gods. One of the most important, Sirius. Sirius was more than just a bright light in the sky. It was the herald of the flood. Each year, just before sunrise in mid-July, Sirius would reappear on the horizon. After being invisible for weeks, its appearance marked the beginning of the Nile flood season. This moment was called the heliacal rising of Sirius, and it was a big deal. It meant the year was starting, the waters were coming, life was about to return. So of course, the Egyptians made sure their temples and rituals were timed around it. But there's more. They didn't just track Sirius, they tracked entire constellations, like Orion, a group of stars that to the Egyptians represented the god Osiris. Osiris was the lord of the afterlife, the god of rebirth, the one who ruled the dead with calm wisdom and a very stylish green face. So when you were building a tomb, especially a royal tomb, you wanted it to point in the direction of Osiris, to align your journey from this life to the next with the path written in the stars. Now let's zoom in on something familiar. The Great Pyramid of Giza. It's not just tall, it's not just impressive, it's aligned almost perfectly with the cardinal directions north, south, east and west. I mean, really aligned, to within a fraction of a degree. Let that sink in. Without compasses, without GPS, without lasers or satellite imaging. They got it almost perfect, using stars. How? One theory is this. They used a method involving two sticks, a plumb line, and the circumpolar stars. Those are the ones that rotate around the North Pole and never set. They would watch two of these stars cross the meridian, that invisible line running north to south, and mark the exact middle point between them. That gave them true north. Then they'd lay out their structure from that reference. Adjust, repeat, take their time. Because when you're building a tomb for eternity, you can't just eyeball it. Now, let's talk about the shafts. Inside the Great Pyramid are narrow passageways not for walking, but for air and possibly for starlight. Some researchers believe these shafts were aligned to specific stars. Orion's belt, Sirius, Thuban, and others at the time the pyramid was built. It's like the pyramid was designed to communicate with the cosmos, or maybe just to guide the pharaoh's soul upward, toward the heavens, toward the stars that were once gods, now companions. Either way, the message was clear. What happens on Earth is just the beginning, and the stars, they're where the journey continues. Now, let's take a step back. Why go through all this trouble? Why align giant stone structures with the sky? Because to the Egyptians, the cosmic order mattered. The universe wasn't chaos. It was massate, balance, structure, harmony. When you built something, it had to fit into that order. A temple aligned with sunrise at the solstice. A tomb aligned with the stars of the underworld. A city grid based on the directions of heaven. It was more than architecture. It was a statement of faith. You were saying we understand, we see the patterns, we honor the design, and in doing so, we become part of it. Now imagine being there, standing at dawn, on a high point, watching the first light touch the horizon, the stars fading, the sky shifting from black to gold. A priest beside you raises a hand and says, "Now," and that's the moment the building begins. When heaven tells earth, "Go," it's poetic, it's precise, and honestly, it's kind of beautiful. So, no, the Egyptians weren't just stacking rocks. They were aligning heaven and earth. They were measuring eternity, with strings, with sticks, with shadows and stars. And when they built for pharaohs, they weren't just thinking about this life, they were thinking about what comes after. Because in the Egyptian view, death wasn't an end, it was a transition, a journey through the stars, and you'd need a well-aligned launch pad. So if you ever feel small under the night sky, just remember, some people looked up and saw structure. They saw math in the heavens, they measured it, and they built toward it. Next time we'll head down from the stars and back into the real world, because now that we've planned everything, it's time to build. Let's talk bricks. Big ones, millions of them, and how to stack them just right without lasers, cranes or coffee. Planning a monument that lasts 5,000 years. Let's build something, not just anything, not a shed, not a tiny temple, not even a nice garden gazebo. No. Let's build a pyramid. A monument so massive, so precisely constructed, so strangely perfect, that it will stand for thousands of years, long after empires fall, long after languages vanish, long after someone invents TikTok and ruins attention spans forever. We're talking about the Great Pyramid of Giza. This thing is big.
Originally over 46 meters tall, that's about a 45-story building made of 2.3 million stone blocks, each one weighing between 2 and 15 tons, not kilograms, tons.
Let's just say this was not a weekend project. But before you move a single stone, you need a plan. So here's the question. Did they have blueprints? Short answer, kind of. Long answer, let's dive in. You won't find rolled up scrolls with pyramid floor plans sitting in a museum, but we do have traces of how they planned. And it starts with the base. First, they chose the perfect spot. Stable bedrock, high ground, not too far from the Nile, so you could ship in materials but far enough to avoid yearly floods soaking your foundation. Because nobody likes a soggy pharaoh. Then came the layout. They measured out a square base, nearly perfect. Each side originally about 230 meters long, with less than 20 centimeters of difference between them. That's a 0.09% margin of error. Try doing that with no steel tape measure. They leveled the ground, and we mean really leveled. Today, laser leveling equipment would struggle to beat how flat the base of the Great Pyramid is. Some think they did this using water, digging shallow trenches and making sure water pooled evenly across the area. Smart, simple, muddy. Next question, how did they know how big to make it? Well, the dimensions weren't random, and they were based on cubits, remember those? 1 cubit are the length from your elbow to your fingertip. For royal construction, they used the royal cubit, roughly 52.4 centimeters. So the pyramid's base? About 440 royal cubits per side. The height? 280. Why those numbers? Good question. Some scholars think it's because the ratio between half the base and the height equals, wait for it, yes, P, as in 3.1, as in math's most famous irrational number. The pyramid might have been a giant stone pi symbol. Accidental? Maybe. Intentional? Possibly. Either way, very cool. Now let's imagine the planning process. A team of scribes and architects, maybe standing in a dusty tent, drawing diagrams in the sand. They use ropes to mark distances, cubit rods to measure. Maybe someone brings out a wooden model. Maybe someone just gestures dramatically and hopes the others are following along. It wasn't blueprints as we know them, but it was careful, mathematical, and methodical. Every block had to fit, every angle had to be right, and every stone had to arrive on time. Speaking of stones, most of the limestone used for the pyramid's body came from nearby quarries, easy enough. But the granite, that came from Aswan, over 800 kilometers away. They floated these massive blocks down the Nile on barges, which means someone had to calculate weight, buoyancy, river currents, loading times, and dock locations. Not bad for a civilization with no calculator. Then there was workforce management, tens of thousands of workers, schedules, tools, food, beer, housing, sanitation. You think planning a birthday party is stressful? Try coordinating a city-sized workforce building a 6 million ton triangle. And yet, they did it. There are even clues suggesting they built scale models before construction. Archaeologists have found leveled platforms near pyramid sites with small stone layouts, like miniature test runs, ancient Lego, and it makes sense. If you're building something that might last forever, you probably want to practice first. Now let's talk orientation. The Great Pyramid is aligned almost perfectly to the cardinal directions north, south, east, west. Less than 0.05 degrees off. That's the kind of precision we'd struggle to get today, even with GPS. How did they do it? They probably used stars, specifically the Big Dipper and Little Dipper, or more accurately, the stars known today as Kokeb and Mizar. By watching them rotate around the North Star over the night and marking where they crossed, they could find true north. Then they used plumb lines and sighting tools to transfer that information to the ground. It wasn't easy. It wasn't fast. But it worked. And that's the theme here. Ancient Egyptian architecture wasn't quick or flashy. It was slow, careful, deliberate, like writing a love letter. They weren't just stacking stones. They were sculpting time, and the math behind it, hidden in every layer. The base length, the slope, the number of steps, the positioning of internal chambers, the angle of the shafts, all of it planned, all of it calculated. This was architecture as cosmic alignment. It wasn't just for show, it was for eternity. You were building a machine, a symbol, a ladder between life and afterlife. And to do that, you had to get the numbers right. So no, we don't have a scroll that says step 1 build giant triangle, but we have the pyramid itself, still standing, still aligned, still whispering the math of its makers to anyone willing to listen. In the next chapter, we'll dive into the weirdly specific mystery of the pyramid's angle, why it slopes exactly the way it does, and what ancient Egyptians used instead of trigonometry. Spoiler, it involves hands. The 51.84 degree mystery. Let's talk about angles. No, wait, don't run. This isn't high school trigonometry. There are no sine functions here. No cosines lurking behind the corner. Just one big question. Why do the pyramids look like that? You know what I mean. The angle. That iconic slope. Not too steep, not too shallow, just perfectly triangular. The kind of triangle that says, I've been here for 5,000 years, and I plan to stay another 5. The Great Pyramid of Giza has a slope of about 51.84 degrees. That's oddly specific. Not 45, not 60, not a nice clean number. Why? And how did they figure that out without calculators? Let's rewind. Ancient Egyptians didn't use degrees. They didn't sit around saying, let's go with a 51.84 degree incline. They used something far more charming. They used their hands, specifically their palms and cubits. This brings us to a magical ancient math term, the Seked. Not second, not skid, it's pronounced like Seked. It's one of those words that sounds like it belongs in a forgotten board game, or a very polite sneeze, but in ancient Egypt, it was serious business. The Seked was a way of describing the slope of a pyramid. Here's how it worked. You start with a cubit's rise. That's about 52.4 centimeters, the standard unit from elbow to fingertip. Then you ask, how many palms out does the pyramid go for every cubit up? 1 cubit is 7 palms. So if a pyramid rises 1 cubit and extends 5.5 palms horizontally, that's a Seked of 5.5. Simple, elegant, visual. It's basically rise over run, but in human body parts, which is kind of adorable. The Great Pyramid has a Seked of 5. That's not a round number, but it turns out that a Seked of 5.5 palms per cubit gives you a slope angle of about 41 point. Coincidence? No way. This was deliberate. Now, did the Egyptians say degrees? No, they didn't even have that concept, but they knew what shape they wanted. They could see that with a Seked of 5.5, the pyramid had a certain height, a certain width, and a certain vibe. And when your whole civilization is about balance, harmony, and divine geometry, the vibe matters. Let's try to picture how they used this. You're a builder. You've got a ramp. You're dragging giant blocks. You don't want the ramp to be too steep. That's a backbreaker. Too shallow. You're building to the moon. So your supervisor, probably a very sunburned scribe, comes over with a cubit rod. He lays it down vertically, then measures out 5.5 palms horizontally. Perfect, he says. Keep the slope like this. You nod. You keep building. You keep dragging. You curse slightly under your breath. But the angle is right. The pyramid is rising. And here's the fun part. Even centuries later, other pyramids used similar slopes, not always exactly the same, but close. Because this angle worked, it was structurally sound. The weight of the stones distributed nicely. The base supported the top, and the shape, well, the shape looked eternal. But of course, not everyone got it right. Let me introduce you to the bent pyramid. This pyramid, built by Pharaoh Sneferu, starts rising at one angle, and then halfway up, it changes direction. The lower part rises at about 54 degrees, then it flattens out to 43 degrees, near the top. It looks like someone started building too steep, panicked, and said, let's just tilt it less and pretend it was on purpose. Why did that happen? We don't know exactly. Maybe they realized the steep slope wasn't stable. Maybe the project manager had a math meltdown. Maybe the pharaoh said, make it taller, and the builders went, sure, but let's not die. Whatever the reason, the bent pyramid teaches us something important. The angle matters. Too steep? Structural risk? Too shallow? Loses that pyramid feel? But 51.84 degrees? That's the sweet spot. Let's appreciate that for a second. Thousands of years ago, using body-based measurements and geometry carved into stone, ancient Egyptians found an angle that balances aesthetic, function, and spiritual meaning. Modern engineers still admire it. Now, let's add a little more mystery. Some scholars have pointed out that the ratio of the Great Pyramid's height to half its base is roughly 1 to pi. So if you took the height and multiplied it by 2 pi, you'd get the perimeter of the base. In other words, the pyramid might be a 3D model of a circle's geometry, a squared-off version of a sphere's shadow, a monument that encodes pi in its dimensions. Is that real or a coincidence? We don't know, but what we do know is this. The Seked of 5.5 produces that exact ratio. Was it intentional? Did they know about? Well, they didn't call it P, but they did estimate circles surprisingly well. The Rhind Mathematical Papyrus, for example, uses a formula that gives P as about 3.116. So maybe they didn't have the symbol, but they had the idea, and they built it into stone. So next time someone tells you ancient people didn't understand math, tell them this. Somewhere, 5,000 years ago, a guy with a stick and a length of rope figured out how to build a 46-meter pyramid that still makes architects sweat, all thanks to a slope measured in palms. In the next chapter, we'll look at the other big question. It's not just how to design the pyramid, it's how to build it. 2 million stones, some as heavy as elephants. No cranes, no trucks, no hydraulics, just ramps, friction and very sore legs. Get ready. Lifting 2.3 million stones with no calculator. So you've got your blueprint, you've got your perfectly squared base, your heavenly alignment, your lovely 51.84 degree slope. Now all you have to do is move 2.3 million limestone blocks, some weighing more than a car, and stack them into a giant triangle. Easy, right? Except no engines, no cranes, no forklifts, not even a wheelbarrow with a squeaky tire. Just stone, sand, sweat, and an endless supply of elbow grease. Welcome to ancient logistics. Let's begin with the basics. Each block in the Great Pyramid weighed between 2 and 15 tons. That's like trying to move a medium-sized elephant, repeatedly, every few minutes, in 40-degree heat, wearing sandals. Most of the blocks were limestone. Quarrying them was fairly straightforward. You'd find a good limestone cliff, carve around the block, hammer some wooden wedges into the cracks, soak them with water, and let the expansion pop the stone loose. Boom. Block. Then you had to move it. Some stones came from nearby quarries, just a short haul from the building site. Others, like the red granite used in the king's chamber, came from Aswan, more than 800 kilometers to the south. That's not a typo. 800 kilometers. How do you move a 15-ton block that far? Answer: the Nile. The river was their superhighway. They loaded blocks onto wooden barges, floated them downstream, then hauled them across land. And no, they didn't just drag them on dry sand. That's incredibly hard. Instead, they got clever. Recent discoveries suggest they wet the sand in front of the sleds. Just the right amount of water makes the grains stick together and reduces friction. Suddenly, a team of 20-30 workers could pull a stone that would otherwise be immovable. Science meets squishy mud. Okay, so you've got your stone at the site. Now what? You stack it. Which brings us to the biggest mystery in pyramid studies. How did they get the stones up that high? There are theories. Oh, so many theories. Let's go through the greatest hits. Theory 1, the straight ramp. This idea says they built a long, straight ramp leading up to the side of the pyramid and hauled the stones up. Simple. But here's the problem. To reach it 106 meters in height with a gentle slope, the ramp would have to be a mile long, and it would require more material than the pyramid itself. That's a hard sell. Theory 2, the zigzag ramp. A switchback-style ramp wrapping around the outside of the pyramid, like a mountain road. Saves space. More manageable. But it would have blocked the view of the pyramid under construction, which doesn't match the evidence. Also, carving perfect edges while dragging stones around corners sounds like a nightmare. Theory 3, the spiral internal ramp. This one's fun. It suggests that the ramp actually spiraled inside the pyramid as it rose. Neat, compact secret. But also, how do you light the inside? How do you turn giant stones around corners? And why haven't we found more clues? Theory 4. Some combo of the above. The most likely answer. A mix. Straight ramps at lower levels. Zigzags for medium heights. Maybe a spiral platform near the top. Adapt as you build. Just like IKEA instructions. Except you're moving 6 million tons of rock. Now, let's talk about the workforce. Contrary to old myths, the pyramids were not built by slaves. There's solid archaeological evidence that the workers were well-fed, well-treated labourers, possibly conscripted during the Nile's flood season, when farming wasn't possible. They lived in organised camps near the site. They had doctors, kitchens, even cemeteries. Some workers got beef, which was a luxury, and most importantly, they got beer. Yes, payment in beer. Daily rations included bread and several litres of beer, partly for hydration, partly for morale, and partly because beer is full of calories and makes pushing rocks slightly less awful. It's entirely possible that the greatest structure of the ancient world was powered by carbs and mild intoxication. Respect. Of course, someone had to keep it all running. The scribes tracked the stones, how many arrived, where they were placed, who moved them, how many workers were on shift. They basically ran the ancient version of a logistics company, Pharaoh Prime. There were also engineers, though they didn't wear hard hats. These were thinkers, planners, designers. They coordinated ramps, angles, lifting techniques. They figured out how to position each stone with minimal error, because if you mess up the base, by the time you reach the top, the whole thing is a disaster. You can't fix it in post when you're stacking granite, so each block was placed with care, lavered, measured, adjusted. Imagine that moment. You and your team haul a block up a ramp. It's sweaty, it's loud, the foreman yells something. You lower it into position, it fits, exactly, and then you do it again, 2.3 million times. That's not just construction, that's commitment. There's something powerful about that kind of patience, that kind of repetition, day in, day out. Not for fame, not for social media likes, but for something that might stand forever. And somehow, it worked. The pyramid still stands. Solid, straight, beautiful, all without modern tech. Just ropes, levers, ramps, wet sand, and beer. It's almost soothing. A reminder that sometimes the biggest things in life aren't built quickly. They're built one small piece at a time, with teamwork, with planning, with a lot of and maybe a little music to keep the rhythm. In the next chapter, we're going to look at something more mathematical, not how they built it, but how they measured it. Because when you're constructing a pyramid, you need to know how tall is it, how wide, how much volume, and most importantly, how many frogs do we need to draw to represent all this? It's time for some ancient math. Don't worry, it's the kind of math you can fall asleep to. Area, volume, and a whole lot of sand. Let's do some math. Wait, don't panic. This is the calm kind of math. The kind whispered by candlelight. The kind scribbled slowly onto papyrus, with a reed pen. The kind that smells faintly of sand and warm beer. Because if you're going to build a pyramid, you need numbers. And not just any numbers. You need to know how big this thing is going to be. You need to know how much space it takes up. And maybe, just maybe, you want to brag to your neighbouring pharaoh about how many cubic cubits your pyramid has. Let's start with something simple. The base. The Great Pyramid's base is a square, about 230 metres per side. That's over 5.3 hectares of area. Or, if you prefer ancient Egyptian units, roughly 440 royal cubits on each side. So to find the area, you do what any scribe would do, multiply length by width. 440 cubits does 440 cubits, a 93,600 square cubits. Nice and neat. That's your foundation, your footprint, the place where millions of blocks will rest. But how tall does it go? Originally, the pyramid stood at 280 cubits high. That's about 46 meters. So now you want to know, what's the volume? This is where ancient Egyptian math gets clever. You see, the Egyptians understood how to calculate the volume of a truncated pyramid. A pyramid with the top chopped off. That shows up in the famous Moscow Mathematical Papyrus, written around 18... But for a full pyramid, with a nice pointy top, the formula is even easier. Volume ia 1/39 base area times height. Did the Egyptians know this exact formula? Maybe not with symbols, but based on surviving texts, yes, they absolutely understood the logic. They knew that if you stack layers smaller and smaller as you go up, the space gets less and less and eventually you reach a point. So, using their numbers, volume there, which equals about 18 million cubic cubits. That's a lot of cubits. Now, let's convert that into something more familiar. Cubic meters. The Great Pyramid's total volume is roughly 2.6 million cubic meters. Imagine that much stone. Imagine it stacked, block by block, day after day, rising into the sky. But here's where it gets more interesting. Let's say you wanted to estimate the weight of the whole structure. If limestone weighs around 2.5 tons per cubic meter, and you have 2.6 million cubic meters of it, that's roughly 6.5 million tons. 6.5 million tons. No cranes, no trucks, no problem. Now imagine you're a scribe trying to track materials. You'd want to know how many blocks per layer, how much stone per side, how much food to feed the workers stacking those blocks, how many jars of beer to prevent mutiny. And you'd have to calculate all that by hand, or rather by papyrus and ink. So what kind of tools did they use for this math? The Egyptians didn't have algebra, no x's, no equal signs, but they had multiplication by doubling, division by halving, and a deep love of unit fractions. Remember those? So let's say a block layer needed 20,000 blocks, and a quarry could produce 750 blocks per week. How long would it take? You double from 3 5,000 to 20. Now, pick the right combination. 750 total, close enough. Call it 6 weeks with a buffer. That's how they thought. Logical. Step by step. And then there's the sand. So much sand. Before you stack blocks, you have to clear sand. Before you build ramps, you need to pile sand. Before you level the site, you have to shovel. Yep, more sand. Engineers estimate that millions of cubic meters of sand were moved during the pyramid's construction, not for the pyramid itself, but for the logistics around it. Ramps, platforms, walkways, quarries, all needed sand work. Now imagine calculating ramp volume. You're building a ramp 500 meters long, 10 meters high, and maybe 20 meters wide at the base. A scribe might model it as a trapezoidal prism. Even if he didn't call it that, he'd estimate surface area, volume, labor required, and he'd do it all using cubits, palms, fingers, and careful multiplication by hand. It's not fast, but it works. Then you'd calculate how much stone you're going to remove once the pyramid is done. After all, you don't want a giant pile of construction junk sitting in front of your masterpiece. So yes, the math wasn't just about building, it was also about cleaning up. Let's not forget about interior chambers. They had to be cut into the structure as it rose. The king's chamber, the grand gallery, air shafts, all required exact placement. Get it wrong, and you've got a 15-ton stone sitting on your sacred hallway. Not ideal. So the scribes and planners had to know the angle of ascent, the number of layers, the alignment of internal features with the outer structure, the total height at each level. Every block mattered, every corner, every cubit. Even the joints between stones were planned. Some are so tight you can't fit a credit card between them. That's not magic. That's measurement. So the next time someone tells you ancient math was primitive, tell them this. It calculated the volume of the largest structure on Earth for over 3,800 years. It moved 6.5 million tons of rock with hand tools. It planned galleries, shafts and ramps with no drafting software. And all of that was written on papyrus. In the next chapter, we'll explore something we've been teasing this whole time, a mystery hidden in the numbers. Was the number pi secretly built into the pyramid? Let's find out. Pi in the pyramids. Let's talk about pi. That beautiful, irrational, infinite number that starts with 3.14t and keeps going until the heat death of the universe. Mathematicians love it. Bakers pretend to love it. And school children fear it. But here's the question. Did the ancient Egyptians build pi into the pyramids? And if so, why? Let's start with the facts. The Great Pyramid of Giza has a base length of about 234 meters on each side. That's roughly 440 royal cubits. Its original height, 146.6 meters, or 280 royal cubits. Now, if you take the perimeter, that's 4 times the base, you get about 901.6 meters. And here's where things get weird. If you take the pyramid's height, 280 cubits, and multiply it by 2 pi, you get that's within less than 1 cubit of the actual perimeter. Which leads to the theory, maybe, just maybe, the pyramid is a stone model of a circle, or more specifically a hemisphere. The idea is that the pyramid's height corresponds to the radius, and the perimeter of the base corresponds to the circumference. So, height, Toki P, base perimeter. And now we all pause and whisper, whoa, was it intentional? Some say yes. But the ancient Egyptians had a practical understanding of pi long before anyone gave it a Greek name. Others say no, that it's a coincidence, that the proportions were chosen for aesthetic or structural reasons, and pi just happened to sneak in. Let's explore both sides. First, the yes camp. They point to documents like the Rhind Mathematical Papyrus, written around 1650 BCE. In it, a scribe named Umes describes a method to estimate the area of a circle. He says, take the diameter, subtract 1/9 of it, then square the result. Translated to modern math, this gives a value of pi equal to about 3. That's remarkably close to the real value, 3.12116, especially for a civilization that didn't use decimals. It shows that Egyptians understood circles. They weren't calculating infinite digits, but they knew how to estimate. So, if a scribe or architect noticed that using 280 cubits of height and a base of 440 cubits gave them that elegant ratio, maybe they saw pi and smiled. Now, the no camp, they argue that the proportions were chosen for practical reasons: stability, aesthetics, labor limits, and any appearance of pi is just a mathematical coincidence. After all, the Egyptians didn't leave us a note saying, "Dear future nerds, this pyramid represents 2 pi times the height. Enjoy." And that's fair. We can't read too much into numbers without solid evidence. But here's where it gets interesting. Even if it wasn't intentional, it's still amazing, because it shows that the Egyptians were working with geometric intuition. They were drawing shape, building ramps, sizing up proportions. And in doing so, they brushed up against universal constants, just by using their eyes, their ropes, and their logic. And that's kind of beautiful. It reminds us that math isn't just about symbols and equations. It's about relationships, between height and width, between circle and square, between earth and sky. Now, let's get philosophical for a moment. Pi is the ratio of a circle's circumference to its diameter. But it also shows up in waves, light, quantum physics, and even probability. It's a number that shows up everywhere, even places it has no business being. And somehow, in the middle of the desert, with no calculators, no decimals, no trigonometry, the Egyptians may have accidentally built it into a pile of rocks. A very large, very perfectly angled pile of rocks. That makes you think, maybe the pyramid is more than a tomb, more than a monument. Maybe it's a mathematical echo, a shape built with such balance and simplicity that it naturally aligns with truths buried deep in the fabric of the universe. Or maybe, and this is also possible, it just looks cool. Now, let's talk about how this theory became popular. Much of the pie in the pyramid idea comes from 19th century British scholars who were a little obsessed with trying to find mystical meaning in everything Egyptian. They'd measure the pyramid, pull out their telescopes, drink too much tea, and start connecting dots. Some even suggested the pyramid predicted the size of the earth, the distance to the sun, and the timeline of biblical prophecy. A bit much, if you ask me, but it shows that the pyramid's proportions are so precise, so tempting, that people can't help but try to find secrets inside them. It's like looking at a perfectly cut diamond and wondering if there's a message in the facets. So, was pi really in the plan? Maybe. Maybe not. But the idea that a civilization 4,500 years ago could build something so precise, so exact that modern people still wonder about it, that's the real story. Because pi or no pi, this structure wasn't slapped together. It was designed, measured, aligned, and built with a kind of quiet confidence that says, yeah, we know what we're doing. And maybe that's the best part. Not whether they knew pi, but that they knew how to build, how to shape, how to balance. That's real math, ancient math, the kind done by iron hand, the kind that leaves behind stone instead of equations. And now, we keep asking questions, keep looking for meaning, keep staring at a triangle in the desert and whispering. In the next chapter, we'll set pi aside and dig into something equally important, what the numbers meant. Because for the Egyptians, numbers weren't just tools, they were sacred. Let's explore the mysterious power of 3, and why the universe, according to Egypt, may have been built out of numerology. Numbers as sacred symbols. Let's slow down for a moment, not to do calculations, not to lift stone blocks, not even to build triangles. Let's talk about meaning, because for the ancient Egyptians, numbers weren't just tools. They were symbols, ideas, powers, almost like little spells with digits. You see, in our world, math is mostly practical. We use numbers to check the weather, measure our shoes, count how many coffees we've had today, and pretend we're sticking to a budget. But in ancient Egypt, numbers had spiritual weight. They weren't just how you measured your grain, they were how you understood the universe. So let's look at the numbers that mattered most. Let's start with 3. 3 was everywhere. It was the number of completion, of unity, a beginning, a middle, and an end. Heaven, earth, underworld, past, present, future, life, death, rebirth. Even gods came in 3s. The most famous trio? Osiris, Isis, and Horus. Father, mother, child. A sacred pattern. Pyramids themselves reflect the number 3. 3 sides if you ignore the base. 3 dimensions. A point reaching toward heaven. And it doesn't stop there. Next comes 4. 4 was the number of order, of the material world. 4 winds. 4 cardinal directions. North, south, east. Temples were laid out in 4s. The world was imagined as 4 corners surrounding a central point. Even coffins were often designed to reflect the number 4, as if anchoring the soul to the known world. Now let's jump to 7. Ah yes, the mystical 7. The Egyptians weren't alone in this. Cultures all over the ancient world saw 7 as a sacred number. 7 days in a week. 7 celestial bodies visible to the naked eye. 7 sacred oils. 7 scorpions who protected the goddess Isis. According to legend, 7 was the number of protection, of magic, of transformation. When a spell needed power, 7 was often involved. So, if you're building a tomb and want to make sure your pharaoh has a safe journey into the afterlife, maybe sprinkle a little 7 into the design, just in case. And then of course there's 12. 12 was structure, cycle, balance. 12 months in a year. 12 hours of night. 12 hours of day. The Egyptians divided the sky into 12 decans, star groups that helped them track time at night. 12 was the number that made calendars tick. And calendars weren't just for organizing feasts and taxes, they were for predicting floods, honoring gods, and aligning with the heavens. So, when you look at Egyptian buildings, temples, pyramids, tombs, these numbers show up again and again. Not just because they're mathematically useful, but because they meant something. They carried weight. You didn't use 4 columns by accident. You didn't make a hallway 7 cubits wide for convenience. You did it because it echoed truth. Truth in number. Truth in design. Now, let's pause and ask, why did they care so much? Because in the Egyptian worldview, the universe wasn't chaos. It was built on Mat, a concept of cosmic order, balance, and rightness. Everything from the stars to your sandals had its proper place, and numbers were part of that order. They were tools for creating Ma'at on Earth. When you aligned a temple to the stars and measured its walls in sacred ratios, you weren't just building a building.
You were rebuilding the universe.
One cubit at a time. And yes, the Egyptians were practical too. They used math to build ramps and record taxes, but they didn't see a conflict between sacred and scientific. To them, it was all the same thing. Measuring the width of a door was just as sacred as reading a scroll of prayers, because both were part of the same divine pattern. And that's what makes ancient Egyptian math feel so peaceful. It wasn't rushed. It wasn't competitive. It wasn't about proving someone else wrong. It was about harmony, creating harmony in stone, in sand, in shadow, and harmony, as it turns out, is a really nice thing to fall asleep to. So as you drift off, imagine this. A scribe sits in a quiet temple chamber. The walls are cool. The air smells faintly of papyrus and oil. He unrolls a scroll, dips his pen, and begins to write. 4 pillars, 12 steps, 3 doors, 7 lamps. He's not rushing. He's not checking his phone. He's writing numbers with meaning. Not to pass a test, not to solve a problem, but to bring a little more balance into the world. And maybe, just maybe, into yours too. In our next chapter, we'll explore a number that isn't about harmony, but about mystery. It's time for the golden ratio. Did the Egyptians use it? Or are we just seeing what we want to see? We'll explore the myths, the math, and the magic of the world's most famous number that no one can quite agree on. But for now, close your eyes and let 3, 4, 7, and 12 drift through your thoughts like a gentle wind from the Nile. The golden ratio, fact, fiction, or pharaoh's aesthetic. Let's talk about a number that's been called divine, mysterious, magical, elegant, overhyped. Yes, we're talking about the golden ratio, that special number hiding in sunflowers, seashells and spiral galaxies, or maybe not hiding at all, maybe just appearing whenever humans want to see it. But here's the question. Did the ancient Egyptians design their monuments using the golden ratio, or is that just something we tell ourselves so we can sound smart at dinner parties? Let's start with the basics. The golden ratio is a number usually written as phi. That's spelled P-H-I, pronounced like phi. Not to be confused with pi, although they're both irrational and oddly satisfying. The actual value? About 1.61803398887, and so on forever. It shows up when you divide a line so that the whole length divided by the long part is the same as the long part divided by the short. Sounds complicated, but it's just a beautifully balanced proportion. In math terms, if A is the longer part and B is the shorter, A, cob A. Now here's where it gets weird. People claim to see this ratio everywhere. In the spirals of nautilus shells, in the layout of tree branches, in the proportions of the Parthenon, in Da Vinci's art, in galaxy arms, in the human body, and of course, in the Great Pyramid. Specifically, they say the pyramid's proportions, height to half the base, give you something very close to phi. Let's check. The pyramid's original height was 280 cubits. Each side of the base was 440 cubits, so half the base is 220 cubits. Now do the math.
Pretty ATT.
Wait, that's not phi, that's close to p divided by 2, but definitely not 1. So where does this phi rumour come from? It starts with a different triangle. Some people draw a right triangle using the pyramid's height and half its base as legs, then the slant height becomes the hypotenuse. Using that triangle, the slant height is about 3056 cubits. So, slant height, half base, a 300 aha, there it is. That triangle has the golden ratio. But here's the question. Did the Egyptians mean to do that? Or did it just kind of happen? That's where scholars disagree. The yes crowd says absolutely. They point out that the golden ratio appears in many natural patterns, that it's pleasing to the eye, that maybe the Egyptians discovered it intuitively while trying to build something beautiful. The No crowd says, hold on, the golden ratio isn't mentioned in any surviving Egyptian texts. No golden spirals, no fancy algebra, no scroll labelled how to aesthetically enlighten your tomb. And honestly, they have a point. There's no hard evidence the Egyptians knew phi. What we do know is that they loved proportions, they loved balance, symmetry, geometry, alignment. They didn't need phi to make something beautiful. They had eyes, ropes, and a strong aesthetic sense. It's possible, maybe even likely, that they found the same proportions phi represents without ever writing the number down. They just liked the look. Let's compare it to music. If you strum a guitar and find a chord that sounds good, you don't have to know music theory to enjoy it. Same with architecture. You don't need math class to appreciate a nicely shaped wall. Maybe the pyramid builders were just vibing. Maybe phi was a happy accident, and that's okay. We don't have to believe that every ancient monument is hiding secret math. Sometimes a triangle is just a triangle, but that doesn't make it boring. Because here's the thing, the golden ratio isn't mystical because it's rare. It's mystical because it keeps appearing. Even when it's not invited, artists rediscover it. Designers stumble onto it. Engineers use it without meaning to. So maybe that's the real story here. Not that the Egyptians knew Fae, but that they built something so balanced, so geometric, so aesthetically powerful, that Phi just showed up anyway. Like a party guest who wasn't on the list but brought snacks, so you let them in. Let's not forget, the Egyptians didn't use decimal places. They used unit fractions like 1, 2, 1, 3, 1, 4, and so on. Their math was written in a completely different language, but their results still incredibly precise. So even if phi wasn't written on papyrus, maybe it was written in stone, in the slope of the walls, in the layout of the tombs, in the silent math of symmetry. It's a nice idea, isn't it? That ancient builders, guided by ropes and intuition, created something that echoes a pattern found in galaxies and sunflowers, even if they never called it phi. So, did the Egyptians use the golden ratio? We can't say for sure, but we can say they used balance, they used beauty, they used proportions that feel timeless, and maybe that's more important than phi ever was. In the next chapter, we'll stay inside the pyramid, but shift from philosophy to funerals, because behind all this symmetry and geometry, someone was buried, and that burial involved some very mathematical logistics. Coffins, corridors, sarcophagi, and sacred measurements. Let's talk about what it takes to prepare a soul for eternity, using math, the math of afterlife logistics. So far, we've talked about the outside of the pyramid, the angles, the ramps, the stones, the sand, but now it's time to go inside, because the pyramid wasn't just a monument to geometry, it was also a tomb, a resting place for a pharaoh, a passageway to the afterlife, a sacred space filled with secrets, traps, and if you believe Hollywood, the occasional curse. But behind the mystery there was something very human, a logistical challenge, because when you're building a giant triangle in the desert, you eventually have to ask, where do we put the coffin? Let's begin with the big picture. The Great Pyramid has 3 main chambers. There's the King's Chamber, located high up near the center, the Queen's Chamber, slightly lower and offset, and a mysterious subterranean chamber, carved deep into the bedrock. Each one required exact positioning, carving, ventilation, access. None of this was done randomly. It was planned. Let's start with the King's Chamber. It's made entirely of red granite, about 5.2 meters tall, 10.5 meters long, and 5.2 meters wide. It's a perfect rectangular box. Inside it sits a granite sarcophagus, carved from a single block, too wide to fit through the chamber's entrance, which means It was placed there before the roof was built. That's your first math problem. You need to calculate the size of the chamber, the size of the sarcophagus, the timing of when to place it, the stress the roof must support. And speaking of the roof, above the chamber are 5 relieving chambers stacked to layers of granite beams designed to distribute weight and prevent collapse. Together they form a sort of early architectural shock absorber. The granite beams are enormous. Some weigh over 60 tons. So again, how do you place them? Align them? Balance them? You need math, geometry, leverage, and a strong back. Now about the chamber's position. The king's chamber isn't at the bottom of the pyramid. It's about halfway up. That placement is symbolic, sure, but it's also structural. Too low, and you risk pressure from the weight above. Too high, and construction becomes difficult. The architects found the perfect compromise: safe, symbolic, and stable. Now let's move to the Queen's chamber. Smaller, less finished, still elegant. Its purpose is debated. Maybe it held statues. Maybe it was symbolic. Maybe it was an earlier burial plan that got upgraded. Maybe it was a spare room, in case the afterlife had guessed. What we do know is that it also required math, precise measurements, alignment with the pyramid's core, ventilation shafts cut at shallow angles that point to stars. That's not random, that's astronomy, geometry, and sacred design all in one. And below it all, the subterranean chamber. It's deep underground, unfinished, roughly carved, a little spooky. Some believe it was the original burial chamber. Others think it was symbolic, representing the underworld. Either way, someone had to design it, carve it, measure it, make sure it didn't flood. Because let's be honest, if your eternal soul is supposed to rise toward the heavens, a soggy basement tomb isn't ideal. Now, let's talk about the passageways. The Grand Gallery is the most famous. A tall, sloping corridor leading to the king's chamber. Its angle, about 26 degrees. That's not random either. That angle allowed for internal movement, placement of stones, and alignment with the inner geometry of the pyramid. The gallery is about 8.6 meters high. Walls perfectly angled, ceiling corbelled. That means each layer juts out slightly to form a high vault. It's not just impressive, it's mathematically precise. Why build it so tall? Maybe to elevate the soul, maybe to guide the pharaoh's spirit upward, or maybe just maybe to let big heavy stone plugs slide down the slope and seal the passage once the burial was complete. Yep, the pyramid had its own security system. Massive blocks weighing several tons were slid into place to seal off the king's chamber. To do that, you needed channels, grooves, ramps, and exact timing. You had one shot to get it right. Too early, and the tomb gets sealed before you finish. Too late, and you're stuck in there with a pharaoh and no lunch. Now let's think about the actual burial ceremony. You'd have priests, scribes, builders, guards, maybe a few nervous cousins. The coffin would be lowered into place. Surrounding it, treasures, furniture, food, sacred items, and scrolls. Each item placed with intention, and not randomly. Items were arranged according to sacred layouts, cardinal directions, and symbolic meanings. You didn't just toss your sandals in next to the mummy. You placed them on the proper side, facing the correct way, because the afterlife was a long journey. And you didn't want to take a wrong turn. Even the size of the sarcophagus mattered. Too big, and it wouldn't fit in the chamber. Too small, and well, that's just awkward. So someone had to calculate internal volume, outer dimensions, doorway clearances, weight distribution, and alignment with the stars. And all of this had to be done with no computers. Just ropes, cubit rods, chalk, and possibly a very nervous foreman. It's amazing when you think about it, that all of these measurements, the angles, the heights, the passageways, were done with human hands. And yet the results feel timeless. Not just as construction, but as ritual. The pyramid wasn't a coffin. It was a machine for eternity, a carefully tuned vessel, a stone spacecraft, a geometric stairway to the stars, and all of it shaped by math. In the next chapter, we'll take a step back. We've explored what the Egyptians did. Now let's look at what happened after. How did their math survive? How did it spread? And why did people forget that Egypt was one of math's true birthplaces? Let's explore the legacy and the mystery of how this ancient math almost vanished from history, how Egyptian math spread and got forgotten. Let's leave the pyramid behind for a moment. Not forever, just long enough to talk about something that's almost as mysterious as the tombs and tunnels. What happened after? After the last stone was laid, after the last offering was made, after the pharaoh was sealed away and the workers went home with sore backs and slightly better beer stories. What happened to the math? Because clearly, the Egyptians knew what they were doing. They calculated volumes, built ramps, estimated angles, aligned with stars. They had systems, techniques, experience, and then, for a while, the world forgot. So, how does that even happen? Let's start with the fact that Egyptian math wasn't just used for pyramids. It was used for everything. Taxes, trade, architecture, astronomy, agriculture. If you were measuring a field, tracking a calendar, or calculating how much barley could fit in a jar, you needed math. And Egypt had scribes who were trained to do exactly that. They weren't just number crunchers. They were the knowledge keepers, the copy-pasters of the ancient world. And for centuries their system worked. But then, history happened. Empires rose. Empires fell. New rulers came in. Hyksos, Persians, Greeks, Romans. And with each wave of change, the Egyptian language evolved. Hieroglyphs became Demotic, then Coptic, then eventually faded out entirely. And with the language, mathematical knowledge faded too. Because Egyptian math wasn't passed down through algebra books or tidy theorems. It was embedded in ritual, practice, and profession. When the priesthoods declined and the temples emptied out, so did the scribal schools. Math wasn't forgotten overnight, but it slowly slipped into the shadows. Now here's where it gets interesting. Just because Egypt stopped writing about math doesn't mean their math disappeared. In fact, it started to spread. The Greeks, especially scholars like Thales and Pythagoras, travelled to Egypt and studied with Egyptian priests. They were blown away. They brought Egyptian geometry home, added their own ideas, and turned it into something more abstract, more theoretical. That's when math became less how many bags of grain can I store and more what is the nature of triangles, which is great. But in the process, Egypt got a little erased. Greek scholars didn't always cite their sources, and later European writers often saw the Greeks as the starting point of math, as if nothing came before. So Egyptian contributions got filed under ancient mystery rather than foundational knowledge. For example, that thing we now call the 3-4-5 triangle. Yet the Egyptians were using that trick 1,000 years before Pythagoras was even born. They used knotted ropes to form perfect right angles, a method still used by surveyors today. But do we call it the Egyptian rope theorem? Of course not. We call it the Pythagorean theorem, and that's kind of how it goes. Egyptian math was practical, functional, quiet. It didn't have flashy symbols or proofs. It didn't try to explain the universe in elegant equations. But it worked. It got the job done. And sometimes that's the kind of math that gets overlooked. Because historians love theory, but ancient builders loved results. Now, centuries later, we've started rediscovering those results. In the 19th and 20th centuries, archaeologists uncovered mathematical papyri, like the Rhind Mathematical Papyrus and the Moscow Papyrus. Inside were problems involving fractions, volumes, angles, and clever solutions. It was like finding the scribbles of ancient homework, and it showed that Egyptian math wasn't just rope and gut feeling. It was systematic. It had rules. Sure, they didn't use algebra, but they used multiplication by doubling, unit fractions, clever approximations of pi. They even had tables for how to divide bread equally among workers. Because math is math, whether you write it with X and Y or with little bird-shaped hieroglyphs. So why did we forget all this? Partly because Egypt was exoticized. In Europe, Egypt became a land of mystery, of temples and tombs, of magic and mummies, but not of math. And once something gets put in the mystical category, it's harder for people to see it as scientific. We love to believe the pyramids were built by aliens, but not by guys with string, chalk and really good planning. But maybe it's time to change that. To remember that math doesn't always have to come from a chalkboard. Sometimes it comes from a quarry, sometimes from a field of barley, sometimes from a rope with 12 knots. The Egyptians gave us a way to think spatially, to work with proportions, to build structures that still stand today. That deserves a little more credit. And maybe, just maybe, it deserves a place in your dreams tonight. In the next chapter, we'll explore how to actually think like an Egyptian mathematician. What did their problems look like? How did they multiply without times tables? How did they write fractions without numerators or denominators? Let's slow things down and learn to solve problems the ancient way. It's time for some calm, sand-covered math. How to think like an Egyptian mathematician. Let's say you're an Egyptian scribe. It's hot. You've got sand in your sandals, and someone just asked you to calculate how many loaves of bread to distribute among 23 workers, using only a basket of grain and a piece of papyrus. What do? You smile, because you're a mathematician. Not the modern kind with glasses and a calculator, but the ancient kind with ink-stained fingers and a deep love for fractions. So let's step into your sandals. Let's learn how to think like an Egyptian scribe. First things first, you don't have numbers like we do. No decimals, no algebra, no symbols for multiplication or division. Instead, you have a base 10 number system, symbols for 1, a special talent for unit fractions, are fractions with 1 as the numerator. So 1, 2, 1, 3, 1, 4, 1, 5. Why? Because that's how they wrote things. If you wanted to say 2, 5, you'd break it down into 1, 3 per 1, 15, or something close enough. It's a bit like writing every recipe using only 1 spoonful of things, just lots of different sizes. So how did they do multiplication? They didn't memorize tables. Instead, they used something called doubling. Let's say you want to multiply 23 by 15. You'd write a table like this.
It's 15.
2, 4, 6. Oh, shit. Now you break 23 into pieces using powers of 2. Then you add the matching rows. 240, 64, 32, 15. A 3. No calculator needed. Just doubling and adding. It's slow. It's careful. But it works. And it works really well if your math is tied to grain, labour or geometry, which it usually was. Now let's talk division. Say you have to divide 9 loaves of bread among 10 people. The Egyptian answer would be, give each person 1. That adds up to... But wait, what about the last? Maybe you turn it into a remainder. Maybe you keep a little for the temple. Or maybe you get creative and make a fractional loaf shaped like a duck. But the point is, Egyptians didn't need perfect decimals. They got really good at approximating. And speaking of approximations, let's talk about how they estimated areas. For a rectangle, they multiplied length by width. Easy. For a triangle, they used base times height divided by 2. Still familiar, but for a circle they had a neat little trick. They took the diameter, removed 1/9 of it, and then squared the result. So if your diameter is 9 units, 9d so the area is about 64 square units. That gives them an effective value of... Not bad for 1650 BC. Now, here's the fun part. They didn't just solve math problems, they wrote them like little stories. Like this one, a man has 7 cats. Each cat kills 7 mice. Each mouse would have eaten 7 grains of wheat. How much wheat was saved? This is like ancient Egyptian math meets bedtime riddle. So how would you solve it? 7 cats. Pick 7 mice. What's 7 grains? Answer: 443 grains of wheat saved, and probably one very tired scribe. Another example. You have a loaf of bread and 4 workers. How do you divide it so that the third man gets twice what the second got, and the fourth gets 3 times what the first got? This isn't just math. It's logic. It's fairness. It's a word problem that makes you want to lie down, which, to be honest, is kind of perfect right now. Because Egyptian math wasn't built for speed. It was built for clarity, for repeatable, understandable, human-scale problems. Not for infinity, not for calculus, but for real life. That's the key. While Babylonian math went big on astronomy and long division, Egyptian math stayed grounded. It helped people measure their fields, split their bread, build their tombs and keep their beer rations fair. And maybe that's why it feels so relaxing. Because it's not about being a genius. It's about being practical. You don't need to memorize formulas. You just need a straight stick, some patience, and maybe a good reed pen. So if someone asks you to divide 10 jars of beer among 7 builders, and one of them insists on getting just a little bit more, you know what to do. Grab your papyrus. Start breaking down those unit fractions, and maybe save 1 jar for yourself, for research purposes. In the next chapter, we're going to step out of the scribal world and into modern times, because the pyramids and the math behind them never really left us. In fact, they're still showing up in movies, books, and wild conspiracy theories. Let's take a relaxed walk through how pyramid math became pop culture, and why aliens keep getting the credit. From pyramids to pop culture, let's take a step into modern times. You're on your couch, popcorn in your lap, a movie playing on the screen, and there it is, the Great Pyramid. Again, somewhere between the explosions, the dramatic music, and someone yelling about secrets hidden in the sand, you realize something. The pyramids are everywhere. They've gone from ancient tombs to pop culture icons. And somehow the math, or at least the idea of math, came with them. So let's talk about that. Let's talk about how the pyramids became movie stars, meme material, and the go-to destination for conspiracy theories. And maybe, just maybe, let's laugh a little too. Because while the real math behind the pyramids is elegant and practical, the math in pop culture, well, let's just say it's got a flair for drama. It all starts with movies. From Indiana Jones to Transformers, the pyramids have been used as everything from secret alien storage to portals to other dimensions. In Hollywood, the pyramid is never just a pyramid. It's always hiding something. A weapon, a prophecy, a forgotten civilization with advanced knowledge of trigonometry and bad CGI. And yes, sometimes it's just a backdrop for dramatic slow motion. But here's what's funny. Even in these wildly fictional stories, the idea of math still shows up. People whisper things like, the alignment is perfect, the angle matches the stars. There's a code hidden in the base measurement. And somewhere, a confused archaeologist sighs, because deep down, pop culture wants the pyramid to be a math puzzle, a cosmic riddle, a giant stone Sudoku placed in the desert just for us. And sure, the real explanation, skilled labor, clever engineering, centuries of refinement, is way more impressive. But it doesn't sell movie tickets. So instead, we get ancient aliens. Let's pause there, because if you've ever flipped through a certain type of documentary channel late at night, you've probably seen it. A man with wild hair and wide eyes saying, I'm not saying it was aliens, but it was aliens.
These shows love numbers.
They'll point to the pyramid's base and say, it's exactly 1/43/200th the circumference of the Earth. Or, if you multiply the height by the square root of Fique and subtract the age of the moon, you get enlightenment. It's math-flavoured mystery soup. And look, it's kind of fun, but it's also missing the point. Because the real miracle isn't aliens. Oh, it's humans. Tired, sunburned, brilliant humans who figured out how to measure, plan, and build something that would outlast empires. Now let's move to books. Over the years, the pyramid has shown up in everything from spiritual guides to thrillers to self-help manuals. Some say it channels energy. Others say it preserves fruit. Yes, really. Still others use it as a metaphor for success. Start at the base, work your way up, reach the peak, and honestly, that one's not bad. Then there's the math side of pop science. Books that dive deep into proportions, alignments, measurements. Sometimes they're very thoughtful. Other times they stretch. For example, the pyramid's angle is 51.84 degrees, which matches the precession of the equinoxes, which is tied to the Fibonacci sequence, which is linked to ancient Mars civilizations. At some point you realize the numbers aren't being used to explain the pyramid. They're being used to decorate a theory. But again, it all comes from the same instinct. People see the pyramid and think, there must be more. And in a way, they're right, there is more. Just not the kind that glows in the dark or beams signals to Jupiter. The real more is how these structures have stayed in our imagination for over 4,000 years. How the math used to build them still works today. How the questions they raise about time, life, death, and precision still fascinate us. Even video games have joined the fun. You've got pyramids in Assassin's Creed, Tomb Raider, and Minecraft. Some are accurate, some are made of gold and filled with lava. But no matter how they're shown, they keep showing up, because the pyramid is a symbol now, not just of Egypt, but of mystery, of ancient knowledge, of geometry and stone. Even in design and branding, pyramids are everywhere. Logos, ads, packaging. Why? Because triangles are stable, strong, clean, and the pyramid is the ultimate triangle. So yes, pop culture has had a lot of fun with the pyramids, sometimes respectful, sometimes ridiculous, but through it all, one thing stays constant. People are still drawn to the shape, the symmetry, the balance, the math of it all. So maybe that's the legacy. Not just that the pyramid is old or big or mysterious, but that it's mathematically magnetic. It keeps pulling us back in. And honestly, who can blame it? It's got good angles. In the next chapter, our final one, we'll wind things down. We've looked at the land, the people, the geometry, the mystery, and the myth. Now, let's step back and let the desert wind carry us towards sleep. Let's recap, breathe, drift. One final qubit. The final qubit. So, here we are. The desert is quiet. The stars above the Nile are gently blinking, same as they have for thousands of years. And beneath them, somewhere just beyond the reach of time, a pyramid stands, silent, steady, and still whispering stories in the language of stone. You've come a long way, from the floods of the Nile to the top of the Great Pyramid, from tally marks to astronomy, from rope knots to numerology, from beer rations to the sacred geometry of the afterlife. You've wandered through chambers, climbed ramps, followed shadow clocks, and stared into the golden triangle of myth and math, all without leaving your bed. Not bad, mathematician. Now, before you drift off completely, let's take one last gentle walk back through it all. Not to memorize, just to remember, softly, you began in the land of the Nile, where floods were calendars and water levels meant life or death. You saw how early Egyptians started to count, not with symbols or equations, but with marks, knots, and grain in jars. Their math was not about perfection. It was about necessity. Then you met the scribes, the original math nerds in long robes with even longer scrolls, keeping track of taxes, bread, and occasionally building plans for world wonders. They didn't just do math, they lived it, through repetition, through stories, through the quiet mastery of unit fractions. Then came geometry. Before Euclid, before textbooks, they stretched ropes, measured shadows, used triangles to rebuild a flooded world each year. They didn't call it the Pythagorean theorem. They just called it doing their job well. You saw how the stars guided them, how the belt of Orion helped aim pyramids, how sacred numbers echoed in temples. 3, 4, 7, 12. Not because of superstition, but because of meaning. Everything had a place, a measure, a proportion, even the soul. You explored the pyramid's heart, stone by stone, angle by angle, sarcophagus by sarcophagus. You saw how precision was not just for beauty, but for eternity. Every passage planned, every chamber calculated, every plug block ready to slide into place at just the right moment. They weren't just building for today. They were building for the forever after. And then you met P, mysterious pi, hiding in the slope of a triangle. Maybe intentional, maybe not, but beautiful either way. And phi, the golden ratio. Not chiseled into walls, but possibly built into the feeling of balance itself. Even if they didn't name the number, maybe the Egyptians still understood its soul. You watched as numbers turned sacred. Math became myth, and temples became equations. Then, in the long, slow fade of empires, the math slipped into the shadows. Not gone. Just forgotten. But not forever. Because you and curious humans everywhere brought it back. Through rediscovered scrolls. Through geometry lessons. Through quiet admiration for a shape that keeps calling us home. And yes, you saw what happened when pyramids met Hollywood. The myths, the aliens, the memes. You laughed a little. You raised an eyebrow. And maybe you even appreciated how a triangle made of limestone could become a pop culture superstar. Not because of lasers, but because of math. Simple, elegant, human. So now we arrive at the final qubit. Qubit number? Who knows? Maybe 20. But here's what it means. You made it, not to the top of the pyramid, but to that calm space where your brain is full, your eyes are heavy, and your thoughts are quieting into sand. You've done enough thinking for tonight. Enough learning. Enough wandering down corridors of logic and corridors of stone. Let the numbers settle. Let the symmetry rest. Let your breath match the slow rhythm of ancient desert winds. And if you feel like you're floating a little, maybe that's just your soul rising through the grand gallery. Don't worry. The ramps are gentle, and the stars are aligned. Thank you for walking through time with me. Thank you for letting ancient math be your lullaby. Sleep well. The pyramid isn't going anywhere, and neither is the math. Good night, sleeper.